नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर आईटी जेई एंड नीट। I feel proud to share with you that one of our student got AIR1 in JEE Mains 2023. This is our JEE Advanced series. Before starting the video of JEE Advanced series, I will like to request you that please like and subscribe our channel एंड डोंट फॉरगेट टू शेयर विथ योर फ्रेंड्स एंड फैमिली। तो आइए शुरू करते हैं जेई एडवांस सीरीज।
Hello everyone, welcome to Chemistry Academy. This is practice set 1 of Electrochemistry in JEE Advanced Series Theory Through Problems. So let us start solving practice set 1. Section 1, this section contains 6 questions. Each question has 4 options for correct answers. One or more than one of these 4 options are correct. And they have mentioned about the marking scheme. So let us go through question number 1. If the cell SCE means saturated calomel electrode, double vertical line means salt bridge AgCN twice minus, whose concentration is 7.5 into 10 to the power minus 3 capital M. Cn minus concentration is 0.025 capital M Ag plus in solid state. Develops a potential of minus 0.625 volt. The reduction potential of given saturated calomel electrode is 0.285 volt. Then the formation constant of AgCN twice minus is 2.303 RT upon F is equal to 0.06 volt. E naught of Ag plus to Ag is equal to 0.8 volt. So first thing is we should know that in this question, when we write that what is the EMF of the cell, EMF of the cell can be written in many form, but in this question, since they have mentioned that the reduction potential of the saturated calomel electrode, so they have given the value of complete reduction potential of saturated calomel electrode, and because of this information I am writing that EMF of the cell can be written as E reduction of cathode. I'm not writing E naught, I am writing E cell. So here naught is not there. E reduction of cathode minus E reduction of anode. Our anode is saturated calomel electrode. The reduction potential of saturated calomel electrode is given. I'm not talking about the standard reduction potential of calomel electrode. It is the reduction potential. So whole value is given. So from here I can put the value. This value is 0.625. From here I can calculate what is E reduction of cathode. The reduction potential of calomel electrode is given, that is 0.285. So from here I can write that E reduction of cathode is equal to minus 0.625 plus 0.285. If I simplify this is coming minus 0.34 volt. So our cathode electrode is on the right hand side, and if I write that what is the reaction taking place at cathode, so the complex compound or complex ion AgCN twice minus in aqueous state will accept one electron to form silver in solid state plus 2 times of Cn minus ion in aqueous state. This is the reaction taking place at cathode. So for this reaction, I know that what is the EMF of this half cell reaction, but I don't know what is E naught of this half cell reaction. So in order to calculate E naught of this half cell reaction, I can use Nernst equation. Before using the Nernst equation, I should write that what is the reaction quotient for this half cell reaction. So concentration of Cn minus ion concentration is given 25 into 10 to the power minus 3. So 25 into 10 to the power minus 3 whole square, that is Cn minus concentration whole square, divided by complex ion concentration. The concentration of complex ion in the system is given, that is equal to 7.5 into 10 to the power minus 3. So from here, if I simplify, I can write that this value is equal to 25. This will be square into 25 divided by 75. And this is 10 to the power minus 6. And this will be 10 to the power minus 4 if I remove this decimal. then this will be 1 by 100. So I can write like this. So on simplification, I can say that this is 3 times, this is 4 times. So this value is equal to 1 by 12. So the reaction quotient of this half cell reaction is 1 by 12. Now I'm using Nernst equation for this half cell. I can write that EMF of this half cell, that is E reduction of half cell, is equal to E naught reduction of this half cell minus 0.06 divided by number of electrons is 1 log reaction quotient, that is equal to 1 by 12. So from here, if I calculate that, what is E naught reduction of this half cell? E reduction of this half cell is minus 0.34 volt, and this will become plus, right? So if I bring it on left hand side, this will again become minus 0.06 log 12. So this is E naught reduction of this value. Now we have to calculate what is the formation constant for AgCN twice minus. They have given reduction potential, standard reduction potential of silver electrode. So now again I can write the reaction where Ag plus ion will accept one electron to form silver in solid state. This is reaction number 1. And the reduction potential here, right? So in this reduction potential, the reaction, this is complex. So if I take this as, if I reverse this reaction, I can write that this is equal to Ag in solid state plus 2 times of Cn minus ion in aqueous state will form AgCN twice plus in aqueous state. This is reaction number 2. If I add these two reactions, I will get formation constant reaction. Ag plus central atom plus ligand will combine to form this complex ion AgCN twice plus. So this is reaction number 3. I'm using the concept of Gibbs free energy is additive in nature. So from there, I can write that delta G naught 1 plus delta G naught 2 is equal to delta G naught 3. Delta G naught 1 is minus number of electrons is 1 Faraday constant E naught 1. Delta G naught 2, okay, so here I think I have missed this electron, 1 electron. So now this is half cell reaction, this is oxidation reaction. So again, I can write that minus N is 1 Faraday constant, and that is equal to E naught 2. This is oxidation potential, right? This is reduction potential is equal to, this is the net cell reaction, which is formation constant. So I can write this is equal to minus 2.303 RT log K formation. So now here, if I simplify, if I remove this minus sign, take the Faraday constant on the right hand side, then I can write that E naught 1 plus E naught 2 is equal to 0.06 log K formation. E naught value is given, right? Reduction potential of Ag plus 2 Ag is 0.8 volt. And we have calculated reduction potential of this electrode, right? Under standard condition, this is reduction potential, but I have to write oxidation potential here. So it will be minus times of this value. So that is 0.34 plus log 0.06 log 12, right? So if I'm writing this value over here, this is equal to 0.34 plus 0.06 log 12 is equal to 0.06 log K formation. So if I take this on the right hand side, I can write that this value is equal to 1.14. On the right hand side, 0.06 will be common, and this is equal to log Kf upon 12, because when it will go on this side, it will become negative, right? So I can write that as log 1 by 12. So if I simplify this, I am getting that this value is equal to 114 divided by 6 is equal to log K formation upon 12, and this value is equal to 19. So from here I can write that Kf is equal to 12 times of 10 to the power 19. If I further simplify, if I multiply it by 10 and divide it by 10, I should write that 1.2 into 10 to the power 20. So for question number 1, we are getting C as the answer. So answer will be C. Question number 2, the electrical resistance of a column of 0.05 molar NaOH solution of diameter 1 centimeter and length 50 centimeter is 5.55 into 10 to the power 3 ohm. Which of the following is correct for the above column? So the first is about resistivity. So we know that resistance is equal to resistivity into L by A. So here the length is given. I have to calculate the area A. Area is equal to pi r square. They have given the diameter. So pi and diameter will be, because the diameter is 1 centimeter. So this radius will be 1 by 2 whole square. So this will come in centimeter square. So this is in centimeter square. So from here, if I calculate that, what is the value of resistivity? So I can put that the resistance in this is equal to 5.55 into 10 to the power 3, which is given here, is equal to resistivity into length. Length between these two electrodes is 50 centimeter upon area. Area is pi by 4. So if I simplify, I can write here that resistivity is equal to 5.55 into 10 to the power 3 divided by 50 into pi by 4, which on simplification I can write that this value should be, if I multiply this by 1000, I can write this 10 will cancel out 100. So this value is equal to 555 divided by 5, which is equal to 111. 111 into 3.14 divided by 4. So if I further simplify this value, I'm getting that this resistivity is exactly equals to 87.135. For more accuracy, in place of 3.14, I can write 22 by 7 and then I will simplify. So I'm getting this value is equal to 87.135 ohm centimeter. So the first option is correct. For the second option, if I am calculating what is B, so we know that conductivity is 1 upon resistivity. So if I take reciprocal of this, that is 1 upon 87.135, which on simplification I am getting this value is equal to 0.01148 per ohm per centimeter. So from here I am getting that B option is wrong, but D option is correct. And once I know the conductivity, I can calculate what is lambda m. Lambda m is equal to conductivity into 1000 divided by molarity. Molarity of this solution is given. Conductivity we have calculated 0.01148 into 1000 divided by molarity. Molarity of the solution is 0.05, which is 1 by 20. So if I further simplify this, I can write that this value should be 1, 2 and 3, 1.48 into 20, which is equal to 14.8 into 2. Here I should write 1148 because 1000 is there. So 3 digit 1, 2 and 3. So 11.48 11.48 into 20, which is equal to 114.8 into 2, which on simplification I am getting this value is equal to 229.6. So C option is correct. I am getting the C option correct. So the answer of question number 2 should be A, C and D. In column 1, select the correct conductometric titration curve, right? So here in column 2, the titration is given, and in column 1, the graph is given. So on the x-axis, we are getting that this is volume of KCl added. ये क्वेश्चन जेई में आ चुका है, ये वाला पार्ट, फर्स्ट पार्ट. So let us try to discuss the concept. In the conical flask, we have a solution of AgNO3, and through the burette, drop by drop, we are adding potassium chloride because this is on volume axis. So we are increasing the volume of KCl in this system drop by drop. So now if I write that what is the reaction taking place in the conical flask, AgNO3 is there. AgNO3 is a salt. Salts are example of a strong electrolyte. They are 100% dissociated. So Ag plus plus NO3 minus ion is there initially in the system. Now, when I am adding KCl drop by drop, during the titration, KCl is acting like a limiting reagent, though it is present as K plus and Cl minus. I'm not writing that because it is going to completely consume. So after the reaction, this is the initial part of the system. After the reaction, there is formation of AgCl. AgCl is a precipitate. So because of AgCl, there is no conductivity or molar conductivity, but there is KNO3. So KNO3 is a salt. Salts are example of a strong electrolyte. They are 100% dissociated. So K plus and NO3 minus ion is there in the system finally. So this is final part of the system and this is initial part of the system. When we are comparing the final part of the system with initial part, this nitrate ion is common. So because of nitrate ion is there initially and finally there is no change of molar conductivity because of nitrate ion. AgCl is a bad conductor because it is in solid state. So the conductivity should change because Ag plus ion is substituted by K plus ion, and both the ions are monovalent, right? Both are cation and both are monovalent. So almost lambda m naught of Ag plus ion is almost equal to lambda m naught of K plus ion. The difference between the conductivity, molar conductivity of monovalent cation Ag plus and K plus is almost equal. So when this titration is going on, during the titration, Ag plus is replaced by K plus. So the change in molar conductivity will be negligible. It will remain constant. But when this reaction is over and again we are adding KCl, there is no reaction. So we are increasing the concentration of K plus ion and Cl minus ion in the system. So conductivity of the system is going to increase. So here the graph given in A option is matching. This is a correct graph. So A option is correct. Same way I can solve for the B option. So when I'm solving the B option, we can say that we have a mixture of weak acid and a strong acid in the system. So in conical flask, we have HCl, which is a strong acid, and we have acetic acid. In short form, I can write this as HAC. And through the burette, microburette, we are adding NaOH slowly into this system. So first, this HCl is going to react. So again, I can write that what is the first reaction happening in this system. So HCl is already in ionized form, H plus and Cl minus ion. And NaOH is coming drop by drop. So NaOH is acting like a limiting reagent. So after the reaction, there is formation of salt. Salts are example of a strong electrolyte, 100% dissociated. And water is a bad conductor. Right. So if I compare here in the system, initially in the system, this HCl is there, and finally in the system NaCl and water is there. Water is a bad conductor. Cl and Cl is common. So we can say that lambda m of the system is changed because H plus ion is replaced by or substituted by Na plus ion. And we know that lambda m naught for H plus ion is very large with respect to lambda m for any monovalent cation, lambda m naught for Na plus ion, right? So because of that, when this titration will go on, initially lambda m should decrease. So lambda m should decrease initially because H plus ion is substituted by Na plus ion. Then when this first reaction is completed and the second reaction will start, for the second reaction, I should write that the weak acid, which will remain as molecular form because of common ion effect also. So this acetic acid, which will exist in molecular form, is now reacting with NaOH. NaOH is coming drop by drop. So during titration, it is limiting reagent. So when this acid is reacting, there is formation of salt and water. So now if I write that in the solution, this is existing in the form of molecule HAC. This is initially, right? Initially, acetic acid is there. Now finally, the salt of acetic acid and water is there. So HAC, which is a molecule, is now replaced by ions AC minus ion and Na plus ion, because water is a bad conductor, right? So there is no effect of water. So we can say that molecule or non-conducting thing is replaced by conducting thing. So lambda m should increase in this portion. So initially lambda m will decrease, then lambda m will increase, and when the second reaction is also over and further will add the base into the solution, then again lambda m should increase, right? So if I write that what should be the graph here, so the graph should be, first it is going to decrease, then it is going to increase, and then it is further going to increase. This is regarding the first equivalence point, and this is regarding the second equivalence point, and this is regarding addition of NaOH without any reaction. We are increasing Na plus and OH minus ion in the system, so lambda m is going to increase. So the B option is correct. B is the correct option. Moving to the C option. In C option, we are titrating weak acid with a strong base. So let us write on next page. We can say that A and B options are correct. Now moving to the C option. acetic acid is initially present. Since it is a weak acid, it will present in molecular form only. The ionized form is very small, we can neglect it. Plus reaction with sodium hydroxide. Since it is a limiting reagent, I am not writing, though it is existing in Na plus and OH minus form. After reaction, there is a formation of salt. So ACNA, and there is formation of water. So initially this molecule is there and this molecule is replaced by this salt and water. This is limiting reagent. So if I compare here, a molecule acetic acid is replaced by acetate ion and Na plus ion plus water. So because of this is non-conducting, non-polar in nature, and this is polar in nature, so conductivity should increase. And after this reaction will completed, and again if we further add, then there is no reaction. So we are adding NaOH, which is existing in the form of Na plus and OH minus. If I draw the graph here, it will increase, and further after the reaction also it is going to increase. This is increasing because non-polar molecule is replaced by ion, so lambda m will increase. And this is increasing because on addition of NaOH, there is no reaction, Na plus and OH minus is added, so lambda m is going to increase. So C option seems to be correct. Moving to the D option, titration between NaOH and HCl, and we are adding HCl. So from the burette in conical flask, there is sodium hydroxide, and through the burette, I am adding HCl. So I should write that Na plus plus OH minus is there initially. I'm adding HCl drop by drop. So this will be limiting reagent when the titration is going on. And then there is a formation of salt, Na plus and Cl minus along with water. So now if I compare, this is the initial condition and this is the final condition. Na plus is common in both. So OH minus is replaced by Cl minus. I know that lambda m naught of OH minus is very large with respect to lambda m naught of any monovalent anion, Cl minus ion. So here lambda m is going to decrease, and after the reaction still we are adding HCl, then lambda m should further increase. So first decrease and then further increase. So here this is wrong. They have shown increasing and then decreasing. It should be decreasing and then increasing. So this option is wrong. So answer of question number 3 should be A, B and C.